Okay, hi everyone. I'm not who is Machiel's host, but I'm going to be able to introduce him. So we're really excited to have Machiel for today. He's here for the rest of today. And Machiel did his PhD at working on networks and even and he did his postdoc at Berkeley, started working on superconducting qubits. I guess he liked that, and then so he decided to continue doing it in professorship where he's now at University of Rochester. So Machiel's work has been focused on using transmons, which are typically we think of as qubits, but using them as qudits. I think that's also what we will discuss today, using superconducting circuits as multi-level. So to give Machiel a little more and
yeah, thank you so much for the introduction and the invitation to come speak here. As Angela already said, the focus of my research on superconducting circuits has mostly been to try to use them for what I did beyond binary quantum information. So encoding multi-level excitations in these circuits that we call artificial atoms. Before we go beyond binary, I just start by thinking about qubit quantum information, binary quantum information, where you have some physical system. I always like to them as spin halves. And if you are able to kind of individually control them and then also couple them together so you can create entanglement, then if you have the right set of operations, you can create what's called a universal quantum computer. And then stringing these gates together, you can do things like quantum algorithms, run quantum error correction, quantum simulation, right? Now, many groups in the world are doing this, and actually the qubit is the most common, right? Many people use different platforms, and every platform has their own different particular challenges. But I would say that to summarize, the challenge in the field right now is that it's just really hard to entangle many of them. And you need many of them to do interesting stuff. So another approach would be to step away from the idea that you encode information in these local two-level systems and you use qudits. You can again use many physical systems. The example here is you could use a Kerr nonlinear resonator encoded in this nonlinear circuit here. And then the idea is that you can build up your quantum computation by having coupled qudits. Now, why would you want to do that? It so turns out that, at least in theory, this will give you very efficient circuit compilation. I cannot give you a one-sentence reason why or how efficient. You have to really study a particular problem, but it turns out that the few theory studies that looked into this, in addition to this log2d scaling factor of just needing fewer qubits to get this to the same size, the main intuitive reason why this is a good idea is that typically what is hard in these quantum circuits is the entangling gate. Usually higher fidelity, they're easier to do. And if you have more information coded per site, per qubit, you just need fewer entangling gates to entangle the whole system. Yeah, that intuitively makes sense. That turns out that you can also do more thorough studies on that. And that is one of the main reasons to use qudits for quantum computation, at least in theory. Another approach might be to use this natural multi-level structure to build in some kind of redundancy, do locally error correction. So you can imagine having a qudit where you do some error correction protocol using all these additional levels, and then you use it to encode a logical qubit. And then you can string those together to form a quantum computation where you have some built-in error correction already. And some examples are doing bosonic encodings, but there's also specific qudit codes to do this. Now, if you think about simulation, it's really tempting to think that if you want to simulate something that is naturally high dimensional, so maybe spin-1 systems or quantum field theories or Kerr nonlinear resonators, it makes sense to have look like your quantum simulator, right? Now, I want to make the point, and this is actually true for all of these protocols, that there is nothing unique about qudits that you could not do with qubits, right? If you want to simulate any high-dimensional analog system, you can Wigner transformation, and you can map it into qubits, and that is universal. The argument is just that maybe it's more efficient and natural if you have a multi-level system that you want to simulate to use these many level systems. And then finally, another area that I'm really excited about is to think of new quantum metrology protocols that you could do. So if you think about a qubit sensor, you can think of a very accurate clock transition, for instance. Then a qubit will have many clocks. And if you have many clocks in one system, maybe you can do things like multi-parameter estimation or more sensitive estimation. And overall, these are all applications that we are looking for. Some of them are funded, some of them we're looking for funding. But that is our motivation in our lab, broadly speaking. We try to develop these circuits to get qu-dit capabilities for all these potential applications. Yeah. Now, you can always ask me about these applications. If we get to talk, you can email me. But for today, we are focusing. We developed the control of the qudits because we had some really interesting results, or at least I'm really excited about them. Results that my students got in the last over the last few months. And so the focus for today is to see how well we can control a qudit in these circuits, with the idea that we can then eventually get these good applications. So I just want to point out that in recent few years, these are all experiments in ion traps, photonic circuits, clear spins, and superconducting circuits. Experiments just from the last few years. qudit experimental realizations have really. So I think it's a super exciting direction. Many labs studying these kind of qudit. Superconducting circuits, because that's what I'm working on. But many of the ideas in terms of control and how you compile and things like that are actually transferable to these other systems. So why are superconducting circuits a natural system to think about encoding qudit? Well, it turns out that the information encoding, even for Q, use quantum bosonic modes. If you think about, we like to represent our circuits in the field in the capacitor, you get a resonance condition 1/√LC. Now, similar to what you would do with a classical field in a cavity, you can quantize this. You put heads in your operators, and it actually is convenient to work with the flux and the charge, the flux through this inductor and the charge across this capacitor, and you get a quantum harmonic oscillator. Now, in reality, this looks a little bit different. This is an example of how you could make such a resonator. We make coplanar waveguide resonators, where if you take a cross-section here, you get electric and magnetic fields between the center conductor and these ground planes. This is kind of like the microwave version of optical. And then we can create boundary conditions here, open and short. Let's create a lambda/4 resonator, and this is our quantum harmonic oscillator. And this is some of the first data that we actually took in our lab in the middle of the pandemic, where students managed 8 of these, couple them to a single waveguide, and then you can measure reflection and phase response. And the important thing is that in this case, we got the Q external, so the coupling of these resonators to the waveguide, to be much lower than the Q internal, which is what you want, because it means that most of your emission from the cavity is to your signal line rather than normal losses. Now, I should state that the 6 or even higher is common. We now managed to do this. But the point here is that you can get really strong coupling and low losses. Quantum harmonic oscillators work very well. If you have a quantum Gaussian states, and those are the most. So you need some form of nonlinearity to get out of these Gaussian states and try to do non-Gaussian state generation. And the nonlinearity that we use is this Josephson tunnel junction, which through the Josephson relations gives you a nonlinear inductance. Physically, it consists of some aluminum with aluminum oxide in the middle, and then on top some maybe we have a problem. I do. How's this? Okay, let's hope that this improves it. So we have these non-linear elements to Gaussian states. Oh, I lost my connection. Yep. And then the simplest way, we don't do this often in practice anymore, is to encode quantum information in either the flux degree of freedom, where you have current paths going clockwise or counterclockwise, so you get a flux pointing up or down, or within the charge degree of freedom, where the number of electrons on this island encodes your quantum information. But the nice thing is that these are circuits, so you can design better circuits that are less sensitive to noise. And the canonical circuit that people use and that I will use in this talk, although we are looking into other qu-dit circuits later, is the Transmon circuit that gives you this cosine potential. And this cosine, you can think of it as approximated from the bottom as an harmonic oscillator, but it has some non-linearity to it. And this essentially gives us these non-equally spaced energy levels that we will use for encoding qu-dits. Yeah. All right, and then the two important parameters that we will investigate are the energy stored in the junction, EJ, and the energy stored in the capacitance, EC. And it turns out that those are actually crucial parameters, specifically the ratio between them, in when you make good qu-dit circuits. So eventually in the lab, we couple these two elements together, our harmonic oscillator or CPW resonator and our transmon. And then this looks a little bit like an atom in a cavity. It's just in the microwave regime. And why do people call this an atom or an artificial atom? I think it's really because you have this spectrum of non-equally spaced levels. It's not much deeper than that. Then we can couple these in the dispersive Jaynes-Cummings regime where they're very far detuned. And then in the qubit approximation, you get the Hamiltonian of the cavity, the Hamiltonian of the qubit, and you get this coupling where the frequency of the resonator depends on the state of the qubit. Now, the nice thing about this system is that for optics, you need to work really hard to focus light very tightly on an atom directions. But these circuits are microwave circuits, and they're millimeter or maybe tens of micrometer size. So getting them is relatively easy compared to nanofabrication capabilities. And this was one of the first times that this was demonstrated in an experiment where they did spectroscopy of the atom or the qubit. And if you do spectroscopy measuring the reflection in the cavity at very low photon number, you see the single peak here that reflects the qubit frequency. But the measurement shows that when you increase the power of the tone that you use to sense, you actually see these multiple peaks. And that's because you start to populate the cavity with a coherent state, and every photon in the cavity actually shifts the qubit frequency a little bit on this axis to the right, but it's actually lowering it in frequency. And so this is resolving individual number of photons in the cavity using the artificial atom, which is, if you think about it, is really an amazing demonstration of how you can do these kind of AMO experiments on a chip. And this was the basis of a lot of success in circuit QED community, where you can now systems and do these kind of AMO experiments. And so we are asking, can we now go beyond this qubit approximation and use these transmons as qu-dits? And to put this a little bit into context, because this is not the first time that this has been done, I like to put this on a scale of the nonlinearity of the system and the number of encoding levels, where a qubit would sit all the way here in the right bottom, very strong nonlinearity, and just two states to encode. And this is also an approach that many industry are taking right now. On the other end of the spectrum, you can also use an almost harmonic oscillator to encode what's called bosonic quantum information. And then to get these non-Gaussian states, maybe that look like this, you need to actually couple this system again to a strong nonlinearity for the control. And if you do that, you can get really amazing error correction experiments done by encoding this system in a very linear oscillator. The challenge here is that to get this control, you need to couple in this external nonlinearity. And this actually gives you a lot of errors that you then need to get rid of again. And so a first step towards using a more nonlinear system is this Kerr paper, where if you look at the frequency spacing of the levels compared to the drive, they are separated, but still control them all. And what we're trying to do in this work is go really in this regime right here in the upper right, where the energy spacing of the levels is large compared to the drive frequency. And then we can really address all these levels individually and encode qu-trits, which has been demonstrated already. I slightly have to update this because people are now going up to the third level, encoding q-quarts. But the point of this talk is to see how far in this regime we can go. Yeah? All right, so that's the background. And now we get to the technical part of this talk where we're asking, how can we climb the Transmon ladder? What are the design questions when you try to go into this regime? And roughly speaking, I will discuss 3 questions. First, how does the noise scale, right? Usually when you make it more complex, it doesn't help you in terms of the noise. The theory predicts at least that there is a bosonic enhancement, which just comes from the matrix elements of the resonator. The further you go, the quicker you lose your information. That's not Transmon specific. That is specific to bosonic oscillators have the same factor. And that predicts increase in the relaxation rate in photon excitation number or qu-dit excitation number. Secondly, there is the question of charge dispersion, and this largely depends on this ratio energy stored in the junction over the energy in the capacitor. And I'll get back to that in just a second. Then the second question is, how many of these states can we read out? Because usually we use this dispersive readout where this is actually plotted similar data, but then the opposite way, spectroscopy of the cavity for different states of the qu-dit. And you can see that if you park your resonator tone at a certain frequency, you can distinguish the phase of the reflected light depending on the state of the qu-dit, and that's what we use for single-shot readouts. But you can only fit so many within the line width of this resonator, and so the question is, how do you go beyond that? And then finally, a natural question is, how many levels can you fit into the Transmon potential? So I'll start with the first question, because them very strongly relate to the circuit parameters that you design, EJ and EC. So let's get some intuition behind the circuit and how this scales. So again, the Transmon is this Josephson junction and a very large capacitor. And if you vary the ratio of energy stored in the junction over energy stored in the capacitor, you see 2 things happen. First of all, the potential will be deeper as you increase EJ over EC. And that means that you can just fit more levels if you EJ over EC. Second, if you look at what we call a charge dispersion graph here, when you plot the energy levels as a function of gate charge offset, then you see that the bottom level is kind of flat. But as you go up and up and up, you see these wiggles. And that means that the transition, any transition going from here to here, the frequency of the transition. And that means that your energy levels will fluctuate and that lead to dephasing. So we call that charge dispersion, and we quantize it by the difference between maybe the bottom and the top of this well here. Yeah. But it EJ over EC uses higher levels. So rest charge noise, you also need to go to very over EC. We can make a plot of what the charge dispersion looks like as a function of EJ over EC for the first transition, the second transition, and the third transition. And you see that they very rapidly drop off. But maybe if you are designing just a qubit, you would go for an EJ over EC of maybe 100, and then your charge dispersion gets in the order of kilohertz or maybe even hertz. And so it's way slower than all the other noise processes. But then if you see that they actually still dephase very rapidly. The image you want to be in for these higher dimensional systems, the order of magnitude 200 for EJ over EC. And that's a regime that's not that well explored. But that's what we set up. We make transmons with very high EJ over EC to get simultaneously a lot of levels in our well and also suppress charge dispersion for these very high levels. Yeah. Now, this was actually an idea that we started about 2020. That's when I started in Rochester. And then the pandemic hit. And so everything shut down. We were not able to do any fabrication ourselves. But we were extremely lucky that Lincoln Labs at the time, a project called Squill, where Lincoln Lab has now a foundry surface where we can chip designs that they then fabricate for us, they send it over, and we can make. So we are very lucky to have used these surfaces. This is a design of a chip that we made, where we make 6 transmons, all coupled to an individual readout resonator, coupled to a readout bus that we can frequency multiplex readout, all 6. And then you can see that the capacitance changes from transmon to transmon. There is, if you would zoom in here, there is a junction somewhere, but that's actually the most microscopic element, or like a few 100 nanometer element, so you cannot see it on this graph. This is a 5 by 5 millimeter chip. And so we designed transmons with different ratios of EJs over ECs. For the experts, if you're interested, these are the parameters. One thing that I forgot to mention, it's actually the most important trade-off, sorry about that, is that as you increase the ratio of EJ over EC, you lose in terms of its non-linearity. So your energy levels become less separated, and that's actually a problem for driving. So that's something to take care of. This argument is true at fixed frequency, though. So the frequency is one other knob that you could use to tune it. But generally speaking, that is the downside. And so these are the numbers for our sample. Right. So to measure these devices that we designed, to then look at all of these 3 questions that I defined in the beginning, starting with the simplest maybe, how many levels can we fit in this transmon circuit? The measurement that we set up to do is kind of a cavity spectroscopy measurement, similar to data I showed before, where if we just send in light and look at its, in this case, actually, we measured transmission, but we could have measured reflection. If you send in a microwave tone at roughly the resonance frequency of the resonator, which is 6 gigahertz, and you detune it slightly, you see that you get this nice resonance curve here in amplitude and phase. But if you do this while you excite the qubit to the first excited resonance frequency, you see that the resonator shifts. In this case, it's shifting by about 200 kilohertz. And then you can do this experiment, preparing the 0 state, measuring at a certain frequency here, looking at the IQ response, and you see that all these single points are single-shot readouts, where the single-shot readout results are nicely separated for 0 and 1. This is the basis of dispersive readout for qubit systems. So far, this is the standard readout technique that people use when they make a qubit. Yeah. But the point is that we designed this circuit. Here's the level diagram, right? Like we do transmission of the cavity, and we populated or not populated the transmon. The point is that now we're using only these first 2 states, but we made a very deep potential well. So let's see if we can go one up. So we can prepare another pi pulse here. So we sequentially populate the transmon excited states, and then for each state we do cavity spectroscopy. And we see that we can also get a dispersive state for the 3rd state, 5th state, 5th state. And it definitely takes some patience to calibrate all of these things. It's easy for me to do here, but the students work really hard in the lab to actually up until, and I'm sorry for the color coding here, it's supposed to say that it's up to n is 10. And then for each one of them, you get like a very distinctive shift. And the ratio of this particular transmon, EJ over EC, was 250. And a rough estimate for how many levels should fit in is square root EJ over 2 EC, which is about 11 for this particular transmon. And so that really matches our prediction really well. Again, I should really plot this on color scale next time, but you can actually notice that for the 10th excited state, it starts to become a little broad. So it starts to degrade as you go outside of this well. But overall, we were super excited to see this data because it shows that we can really at least control all of these states and then dispersively see a shift of the cavity. And then if I plot this data in a slightly, I want to make an analogy to the strong coupling experiment that I showed all the way in the beginning, because these are kind of mirror images of Kerr was doing qubit spectroscopy, resolving the cavity states that were coherent. This is the opposite, where we do cavity spectroscopy, resolving the different states, and they're Fock. And that is really the strength of this particular approach, that because we have energy levels separated, we can actually prepare Fock states which is really different from getting these coherent states. Yeah. All right, so we have shown that we can control up to NS10 Fock states consistent with the EJ over EC. Next question is, can we actually read them out? And we will use the same dispersive interaction that I showed before. And this is now data from our lab where we park the readout tone at this particular frequency. And we can distinguish state 0, 1, 2, and 3 from all the others. But then you can see that there's a problem because the response of all these other states, both in amplitude and in phase, kind of looks the same. So they all overlap on the same blob. So this is a readout, a single shot. Yeah. To roughly measure 4 states, which had been shown in literature before. And we get this in this case with a readout assignment fidelity of about 90% fidelity, although we later improved this in the lab already. I don't have to. If you would do the same thing at a different frequency, you would be able to distinguish 4 other states, for instance, 3, 4, or like everything below 3 and below, 4, 5, and 6 and above. And then you can do the same thing for these higher states. And these are individual readout tones that can distinguish Fock states in small. Yeah. So this is not quite single shot readout of the full Hilbert space, but usually you would want to solve at the same time. And so what we do is we turn on all of these tones at the same time, and then we do something like we think we pretty fairly understand. And so what we have demonstrated is that we can do 8-state readout using 3 tones with a fidelity of around 80%. And we understand a few things that are have room for improvement. The current measurements are done in transmission, and that means that you lose half of your signal. So going to reflection would be better for that. And then also, it's not a full 2-pi phase shift, so that means that we're not quite in the overcoupled regime. And that is because the samples from Lincoln Labs did not have the quality factor that we expected they had. So we can design this a way to go into the overcoupled regime where all of the information leaks out into our system. We are confident that we can increase this. Also, it's actually really interesting readout dynamics. So that's also something that we're exploring. What happens if you have this coupled driven? Lots of questions. All right. So then I wanted to play around a little bit. I asked my students, can you just do the exact same experiment, but instead of doing a pi pulse in the beginning, do a pi over 2 pulse? Because now what you get is you transfer half of the population all the way up the ladder, but the initial 50% stays in the ground state. And here you can already see through cavity spectroscopy that we created a superposition between 0 and in this case 10. Yeah, we didn't do quite state topography of this. We didn't really prove it, but definitely what you would expect to happen happens because half of the population stayed here in the ground state and the other one went all the way to the excited state. So this is a very non-classical state that we prepared here. So then another fun experiment that we wanted to do, I wanted to see Transmon spectroscopy, to do a measurement where we can see all of these transitions. And if you think about it, that's actually kind of hard because the Transmon usually sits in its ground state. So without doing something, if you would just excite like the transitions over here, if there's no population, there's no way to see. So how can we see the Transmon qu-dit spectrum? We came up with this measurement. We used the we already have, so it's a little bit cheating because you already know where it is, but it makes it. So we prepared that these are all even states. And the nice thing is that now we can measure this and we can, instead of evaluating the photon, and now if you do not do anything, you will get even parity because all of them. But now as soon as you hit any transition, for instance, a 0-1 transition, the state will move a little bit from 0 to 1. And so it will become a little bit more odd. Yeah. And so you should see that in the measurement result. Similarly, if you hit the 1-2 transition, the 2 state should go a little bit to 1. And you can convince yourself that every transition in the spectrum that you hit will actually make this a little bit more odd. And so this is now a way to do a single frequency sweep and try to see the spectrum of the track. So sweeping a tone in different time and frequency here, you see the chevron pattern. That is, if you take a cross section here, you see the Rabi oscillator. Because we are plotting this in terms of the parity, you can see that normally it's even parity, but then as we hit the transition, we go a little bit more odd. We can also see the 1-2 transition. We can go all the way up the spectrum, spectral plot, where this local oscillator problem, we're sweeping across the full bandwidth of a mixer with the yellow in the middle. But really, we can do spectroscopy of this whole system. And this also exemplifies the part efficiency argument, that this is a single drive line that we use all of these transitions. So that's a really nice argument as well. It's efficient in terms of readout electronics and drive lines. All right. So with that, we have shown that we can up to 8 states. We know that we can populate the Transmon potential. But now, how about the noise? The methods to control and to read out these circuits. And so now what we can do is we can prepare the Transmon all the way in the excited state, and then as a function of time, watch it fall down. So this is like a T1 measurement for the 9th excited state, but we measure all of these, the population in all of these states. And you can really see that first it leaves the 9th state, and it tumbles down the ladder until it reaches the ground state here. You could fit this with a set of rate equations, the individual rate transition. So we did that, and then we plotted this in a histogram. The experts who have worked with these kind of circuits, you know, T1 is not a single number. You need to average a lot. Experiments is pretty quiet. It's these histograms where in this case, for the first excited state, we get like 40 plus microseconds. And then as you go up the ladder, the energy relaxation rate increases, but not by too much. It's not too bad, I would say. Again, for the experts, this was a run from the Lincoln Labs fabrication where there was a known issue. And so they understand why this was only 40 microseconds. And the fabrication process, there's nothing about the qu-dit design here that should limit, as far as we understand, these T1. So we are hopeful to get this up to 100, 200 microseconds. Lincoln Labs usually is. They convinced us that this was a problem with all of the runs. And I think actually some of you here had the same issue. But we're really interested mostly in how this scales, because the hypothesis is that if we now increase the T1 of the first excited state, all of them become better. And we see that it roughly follows this linear behavior that was predicted by the bosonic enhancement. So that's pretty good. Now then, how about the phase coherence or the echo? In this case, we do, for each single subspace, we do an echo rotation. And that is actually an interesting question. How do you efficiently characterize these multi-level systems? I don't think the best way to do it. I think there should be really cool qu-dit measurements that you can do, or you can kind of do simultaneously in echo. So we're thinking about that. But for now, these were just single subspace echoes. And because eventually you leak out, as you do an echo here, you also leak out. This is much more limited by T1 than a conventional echo. So this is like a lower bound of the actual defacing. And with some maybe outliers, you know, it's not terrible. So we can definitely do coherent operations on these. We don't understand how this one could be longer than the bare T1 here. That's something we still need to investigate. All right, so that is the energy relaxation and the echo defacing time. But there's also the run time. That should depend on the charge dispersion that we talked about all the way at the beginning. So we wanted to verify this prediction that EJ over EC Transmons, where all the way at the beginning, where we have the energy states as a function of gate offset charge. And something that very often happens, not necessarily classical noise moving you along this charge, but quasi-particles can come across the junction, your gate charge by 1. And then a common way to plot it is to draw the even and odd. This process is really measurement averages over many of these jumps. So typically when we do a measurement of the energy transition here, which we do with this Ramsey, we kind of sample both the, at the fixed offset, we sample both the odd and the even band here. Two distinct qubit frequencies. But I say qubit here, and this is actually a problem, because if we would do this in the qubit space, so in the subspace 0 to 1, we have designed our circuit, I mean, it's not even visible here, for the charge dispersion to really be way below all the other timescales. So we cannot use the conventional 0, 1 Ramsey spectroscopy, because the system would have relaxed but before we can measure the tiny difference for the 0-1 transition. And so we want to resolve energies of a hertz, but our coherence, which would require coherence time in the order of seconds. So we do not have that. It's good. It means that this transition is not limited by it, but measure it. So what do? Instead of measuring this charge dispersion between the 0-1 transition, we can go all the way up to the higher transitions and measure it there, because they should be more sensitive. So we can, for instance, go to this 3-4 subspace where we expect to resolve energies in the order of 10 kilohertz, which should be possible within the lifetime of the qubit. And so that's what we do. This is the realistic plot for the prediction of the charge dispersion here for all these levels. And you can see that the 3-4 transition actually starts to become a little bit wiggly. So we measure those wiggles here in a Ramsey experiment in the 3-4 subspace, where you can distinctly see this beating, and corresponds to the frequencies that the system can have. It corresponds to an odd or even difference of quasi-particles across the junction. We can repeat this experiment many times, because as we do this, the gate charge offsets will actually drift. And so this beat will also drift. So we repeat many of these Ramsey experiments and then do them as a function of time. And then you can see as a function of repetition number, you get different detunings from a center frequency, different beat frequencies here. And we do this for the 3-4 subspace and the 4-5 subspace. And notice that these are plotted, these are different experiments, but they're plotted on the same y-axis. And you can very clearly see that the 3-4 subspace has this maximum beating, which corresponds to the maximum difference between odd and even, that's at a given gate charge, whereas the 4-5 space has much larger fluctuation. And this gives us two numbers for the charge dispersion. You only need to measure the maximum once, and then you know what the charge dispersion is. That's the idea. And so now we can compare these numbers to prediction from theory. These are the theory plots that we have right here. And we did this for two different trends, a different EJ over EC. And note that of uncertainty on them, but that's so small. A little bit. It does follow this pattern. And so this gives us a lot of confidence that we activity of qubits to going to very large EJ over EC. Yeah. Summarizing this characterization of the Transmon spectrum, if you are not an expert and you lost me somewhere, this is the time to pay attention again. We can measure 11 energies levels of the Transmon. We can read them out with simultaneously readout tones, distinguishing 8 shots and single shot readout. And we think we have a fairly good understanding of United state noise, at least the energy relaxation scales with the bosonic enhancement factor that we predicted. And we have shown that we can suppress charge dispersion by going to very high EJ over EC. And this very high EJ over EC regime happens to be the regime where we can get a lot of levels in this Transmon. So, we're very excited to think of next things that we can do with this system. We control so many levels within the same site. And so I will have about next steps before we get to questions. Projects to use these systems for the applications that I just mentioned, specifically funded. We have a project to look into bosonic encodings, where really the idea is that if we do bosonic quantum error correction nonlinear systems, we get around the problem of needing an external nonlinearity to control them. And so we hope to create like cat states and other states with very high fidelity and have this very accurate control. And then we're asking, how do you do error correction or bosonic error correction inside the system? We are also looking at efficient circuit compilation to verify the theoretical predictions that if you do this, if you do a same algorithm or an algorithm of the same complexity with qubits compared to qudits, to actually get a benefit. And then finally, we have a project funded to study quantum field theory simulation. On the experimental front, we have other designs of high EJ over EC transmons, where we are starting to look at coupled systems, looking at entangling gates and looking at algorithms. We are also testing different shapes and forms where it doesn't really print out very nice. This is a chip design that we send off where we changed the particular geometry to aim for the same capacitive energy. But then what you can do is you can electromagnetic simulations to predict how the fields look. And then the game is to have as few of the Transmon fields inside of lossy materials. But this is actually an interesting question because it's usually done for qubits, and they have a single frequency that you care about. But our qubits are nonlinear systems, and we care about a range of frequencies. So how do you model the electromagnetic field of this nonlinear oscillator? How do you approximate this for energy participation? Those are questions we want to answer, all these different designs. Finally, we have a project that is led by my student Liz, she's actually already mental data, where the idea is that we apply many of these drives to go from a 0-1 encoding, so a qubit encoding, to these bosonic logical states, or in this case, the binomial encoding, see if we can do error correction. And we are already measuring some of these Wigner functions in the lab, something we're excited about. And if you happen to be at March meeting, Liz is actually giving a presentation on the results there. So please go check that out. And then finally, we have a project that is tangentially related to the qu-dit work because it is actually motivated to do coupling of superconducting circuits to spins. But the project is to make these high impedance niobium spiral resonators that also give you more freedom if you include them into a Transmon-like circuit or maybe fluxonium or IST circuit. And then if you look at the spectrum, without going into too much details, it turns out that you can get suppression of charge dispersion without sacrificing the nonlinearity. So they are a new element that we can add and a new parameter that we can tweak to get maybe even better qu-dit circuits. But the first step we did was to make these very high impedance spirals. And we get impedances of about 3 to 7 kilo ohms with decent quality factors. And it's a project that my student me is leading. So that's what I wanted to talk about today. This is our lab. These are the students that are doing all the hard work. And I'd like to thank you for your attention, and I'm happy to take any questions. Yeah, so the question is the paradigm for two-tone spectroscopy. The first challenge with doing two-tone spectroscopy is that if you do two tones, Transmon end up. No, the opposite. You position with it. Imagine you do two-tone spectroscopy, and you see the first transition, right? Right. You see the transition for the two-tone spectroscopy, but now it's kind of in the ground state, so you see nothing. And that's so the problem is that two tones are not enough to excite the system in the states where you want to see. So that's why it was a little bit cheating, because we need to prepare a state that's already been it required us to know what it was. At least visually, it is a simple measurement where we sweep a single parameter and we measure a single parameter, and it allows us to see the whole spectrum. And the problem is just that if you don't populate the states, you cannot see them. So you need to populate them first, and then you can.
Okay, I have a question. So when you showed the chevrons for your different transitions, the Rabi rates for them seem to be quite different, and it's not like a kind of monotonic scaling or anything like that. So what determines the Rabi rates for the different transitions that you were looking at?
Yes, that's an excellent question. If the same power would be, then you would expect like another bosonic scaling. So you would actually expect the Rabi rate to increase either linearly or with a square root n. The problem is that all things are not equal. So I think it's just power dependent, a frequency dependent power thing, where we can't really tell and I think it's the mixer that determines it in our case. But I think if we would have a really flat drive transmission, both the transmission line and the mixer being really flat in frequency space, but then we would be able to observe the scaling. And we actually were really interested in that because that might be a nice way to measure directly the matrix elements. But actually shouldn't be exactly according to the bosonic scaling. They should deviate a little bit. So, but we couldn't do it because there was too much dispersion on the lines. Yeah.
And I think there was someone that asked if you could do virtual Z-gates using qudits.
Okay, so can you do virtual Z-gates with qubits, qudits? The answer is yes. It's actually very similar to how you do virtual Z-gate qubits. The way I like to think this is that a virtual Z-gate is just you're just checking your frame of reference, and you're doing that. What are you doing that compared to? It is the drive frames, because we have all these distinct drives. And so we can change our reference for each drive individually, which amounts to a phase update of the pulse of every transition. And that gives you virtual Z-gates for every transition. Now they couple together in some way because you actually change the difference of your reference between two states. And so you need to work out up the ladder, but it works, and you full over the Z component because we drive every transition individually. And the nice thing is, and into showing this, is that in principle, they should be limited by your analog resolution, either in time or in voltage of your microwave sources, which is insanely precise. So people have shown for qubits that you can get to unmeasurable infidelities. I think it's, I don't know how high people went, but like definitely below -5 or 6. Which means that we can do things like a snap. It's actually really hard in linear oscillators for free. So that's a good question. What gives you universal computation? There's many approaches to this, and actually it's a really rich question. The easy answer is that if you have individual subspace control, you already have universal control over a qudit, and then I think any entangling gate will get you there. Specifically, if you have virtual Z-gates where you can get these arbitrary rotations. But now the question is, what is a good, or what are better sets of universal control? And one thing that we are doing is looking at displacement gates that actually operate on the whole Hilbert space simultaneously, because this has been shown to be universal for bosonic systems, right? A displacement plus a snap gate or a virtual Z-gate across all levels is universal. And so translating that actually, then the virtual Z-gate you get for free with very high. And it turns out if you just what's called a spin displacement gate, you also get universal control. And to do a universal rotation on the same gate, you need around D pulses, which is actually very favorably if you think about it. So that's actually what my student Liz talked about at March meetings. So, yeah. Oh, and then sorry, yes, and then for the entangling, that's still looking into, like